Have you ever gazed up at the night sky and wondered about the origins of the universe? This vast expanse of stars and galaxies began from a single point, an event so monumental that it set the stage for everything that exists today. This opening act is known as the Big Bang, a theory that offers a compelling explanation for the birth of the cosmos. The Big Bang theory isn't just about a colossal explosion, it's a scientific framework that describes the early moments of the universe. From a singularity, an unfathomably small and dense point, our known universe started to expand. This expansion continues to this day, influencing the structure and behavior of all cosmic matter. Understanding the Big Bang is like putting together a cosmic puzzle. Each piece represents a clue about the universe's origins, its current state, and its possible future. By exploring this theory, we embark on a journey back in time, to the very beginning of everything. It's a story not just of science but of incredible imagination and relentless curiosity. The Big Bang theory posits that the universe began approximately 13.8 billion years ago. Before this moment, there was nothing. No stars, no galaxies, no planets, nor even atoms as we know them. This moment, where everything began, marks the frontier of our scientific knowledge. At the very instant of the Big Bang, the universe was an incredibly hot and dense point. This point, known as the singularity, expanded explosively, creating space and time as it stretched. This expansion was not a conventional explosion but rather a rapid stretching of the universe itself, which continues to expand even now. This theory was initially met with skepticism. The term Big Bang was actually coined by Fred Hoyle, a critic of the theory, intending to mock the idea. Despite its humble and somewhat contentious beginnings, the Big Bang theory has become the cornerstone of modern cosmology, supported by multiple lines of empirical evidence. In the first tiny fraction of a second after the Big Bang, the universe underwent a rapid expansion known as inflation. During this period, the universe expanded faster than the speed of light. This brief but critical phase smoothed out the cosmos, setting the stage for the universe's large-scale structure. Following inflation, the universe continued to expand but at a slower rate. It was filled with a hot, dense soup of particles, primarily quarks and electrons, colliding and combining frenetically. This era is crucial because it set the foundational conditions for everything that followed in cosmic history. As the universe cooled, these particles began to combine into more complex forms. Protons and neutrons formed within the first few minutes, and within about 380,000 years, atoms began to take shape. This cooling phase marked the transition from a particle soup to a more structured universe with distinct elements. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, CMB. This is the afterglow of the Big Bang, a faint cosmic signal that fills the entire universe. It was first accidentally discovered in 1965 by Arno Penzias and Robert Wilson, who initially mistook it for noise in their radio telescope. The CMB is remarkably uniform, suggesting that it originates from a time when the universe was hot, dense, and evenly filled with energy. However, slight variations or ripples in the CMB provide clues about the distribution of matter in the early universe. These ripples are critical for understanding how galaxies and other large structures eventually formed. Studying the CMB has allowed astronomers to calculate the age of the universe, understand its composition, and explore the dynamics of its expansion. This cosmic relic continues to be a primary area of research in cosmology, offering insights into the infant universe that no other evidence can provide. In the moments following the Big Bang, the universe was too hot for any stable atoms to exist. As the universe expanded and cooled, conditions became ripe for the first elements to form, a period known as nucleosynthesis. This primarily involved the formation of hydrogen and helium, the two lightest elements. These initial elements were critical for the structure of the universe. Hydrogen and helium gas clouds are the fundamental building blocks from which stars and galaxies are formed. Without this initial phase of element formation, the complex chemistry needed for life as we know it could not exist. The process of nucleosynthesis is tightly coupled with the predictions of the Big Bang theory. The relative abundances of hydrogen, helium, and other light elements in the universe match what we would expect from a universe that began as a hot, dense state. This consistency between observation and theory is a striking validation of the Big Bang model. Following the era of nucleosynthesis, the universe entered a period known as the Cosmic Dark Ages. This phase began roughly 380,000 years after the Big Bang, after atoms formed but before the first stars ignited. During this time, the universe was filled with neutral hydrogen gas, absorbing any light and making it opaque. This period is crucial because it set the stage for the formation of the first stars and galaxies. The gas clouds began to clump together under the force of gravity, gradually growing denser and hotter. These conditions eventually led to the birth of the first stars, events that ended the Cosmic Dark Ages by reionizing the surrounding gas and making the universe transparent. The light from these first stars helped to clear away the fog of the Dark Ages, allowing light to travel unimpeded across the cosmos. The end of the Dark Ages marked the beginning of the reionization era, a pivotal chapter in cosmic history that set the stage for the formation of more complex structures. As the first stars began to shine, gravity continued to sculpt the distribution of matter in the universe. Over millions of years, stars grouped together to form the first galaxies. These galaxies would become the cosmic building blocks of larger structures, such as galaxy clusters and superclusters. The process of galaxy formation is driven by the gravitational attraction between masses. As galaxies formed, they created deep wells of gravitational potential that drew in more gas and dust, leading to the formation of new stars and the growth of the galaxies themselves. Studying the formation and evolution of galaxies is crucial for understanding the large-scale structure of the universe. Galaxies not only host stars and planets, but also contain dark matter and play a fundamental role in the dynamics of the cosmos. Their distribution and interaction provide valuable insights into the past and future of the universe. While the Big Bang theory explains much about the visible universe, dark matter and dark energy remain two of its biggest mysteries. Dark matter, which does not emit light or energy, is thought to make up about 27% of the universe. It plays a crucial role in holding galaxies together and influencing their formation and evolution. Dark energy, making up approximately 68% of the universe, is even more mysterious. It is believed to be responsible for the accelerated expansion of the universe. Unlike gravity, which pulls objects together, dark energy pushes them apart, working against the gravitational pull of matter. Understanding these components is essential for a complete picture of the universe. They are not directly observable, but influence the movement and behavior of galaxies across vast distances. Solving these mysteries could provide profound insights into the fundamental forces and the ultimate fate of the universe. The Big Bang theory has profoundly impacted modern astronomy, providing a coherent framework for understanding the universe's evolution. It connects the physics of the smallest particles to the movements of galaxies across vast distances. Modern technology, such as telescopes and satellites, has allowed us to test and refine this theory like never before. With tools like the Hubble Space Telescope and the upcoming James Webb Space Telescope, astronomers can observe the most distant galaxies, giving us a glimpse of the universe shortly after the Big Bang. These observations help refine our understanding of how the universe has evolved over billions of years. Moreover, the Big Bang theory also stimulates questions about what came before it and what lies outside the observable universe. It challenges us to think beyond our cosmic horizon and continues to inspire both theoretical and practical explorations into the nature of space and time. The Big Bang theory is not just a story about the distant past. It is a living, evolving framework that continues to influence how we understand the universe. From explaining the cosmic microwave background to the formation of galaxies, it provides a basis for the interconnectedness of all cosmic phenomena. As we continue to explore the universe, the Big Bang theory guides our understanding and frames our questions. It challenges us to think broadly about the nature of matter, energy, space, and time. The ongoing quest to understand the universe is a testament to human curiosity and the desire to find our place in the cosmos. In embracing the Big Bang theory, we not only uncover the origins of the universe, but also appreciate the grand scale and profound mystery of everything that surrounds us. It is a journey that connects us with the cosmos in the most fundamental ways, continually inspiring awe and wonder.